Hello APC Mechanics students, today we will solve the past paper FRQ 2011, exercise 2. An amusement park ride features a passenger compartment of mass m, capital M, that is released from rest at point A, then at the point A the speed is 0, as shown in the figure above, and moves along a track to point E. The compartment is in free fall between points A and B, which are a distance of 3r/4 apart, then moves along the circular arc of radius r, points B and D. Assume the track is frictionless from point A to point D, and the dimensions of the passenger compartment are negligible compared to R. So basically from A to D we don't have friction, so at any position belonging to A and D we can apply the conservation of energy. On the dot below part A that represents the passenger compartment, draw and label the forces, not components, that act on the passenger compartment when it is at point C, which is at an angle theta from point B. Remember that the FBD can vary from one location to another, and it depends where we're sketching the FBD. Basically we're sketching it when the compartment is at point C. So because the compartment is of capital mass M, then it will be submitted to the pull of gravity downward and the normal push, which is perpendicular to the track, and it will be along the radial direction. Then that's the pull of gravity. And let me name it to be Fg, and the normal push would be perpendicular to the track, which is represented by this dotted line, which is something like that. And that would be the normal push. Now in terms of theta and the magnitudes of the forces drawn on part A, determine an expression for the magnitude of the centripetal force acting on the compartment at point C. If you need to draw anything besides what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figure in part A. So basically we need to determine the expression for the centripetal force, which is given by Fc, which is basically the net forces acting along the centripetal direction. And remember that this is a tricky part because we need to consider the magnitude. Now, because the positive direction is toward the center is supposed to be somewhere here, then the normal push would be greater than the component of the gravitational pull along the centripetal direction. Then if you consider Fn minus the component of Fg, that would be by itself the magnitude. Why? Because toward the center, this is the positive direction, we're assuming that, or Fn is greater than the component of Fg. So suppose, for example, if we do the component of Fg minus Fn, that would be a negative answer. We need to add a negative sign in order to get the magnitude. Then that would be the normal push with no projection because it's completely toward the center. And now we need to project the gravitational force. In order to do that, we need to utilize the angle that the pull of gravity does with the radial direction. So in order to do so, I will do an additional FBD here because we're not allowed to add anything here. So basically that's the compartment, and that would be the radial direction. Now that's the pull of gravity, which is downward. And that's the normal push toward the center. And here, if you notice carefully, the normal push along the center direction. Now this is a horizontal, which means that the normal push makes an angle theta with the upper horizontal. So upstairs, I will sketch a horizontal. So basically the normal push here makes an angle theta with the horizontal. And I will also represent here another horizontal. So because the normal push here makes an angle theta with the horizontal, which means that this is also theta. Now notice that this is a horizontal and this is vertical. Then if this is theta, then this is pi by 2 minus theta. Why? Because recall that whenever we have two angles that sum up to 90, if one of the angles is theta, the other would be pi by 2 minus theta, and if one of the angle is pi by 2 minus theta, the other would be theta. And also notice that if this is the centripetal direction, which is perpendicular to the direction of the compartment, if this is pi by 2 minus theta, then this is also theta. And now we're ready to project the pull of gravity along the radial direction, because if this is the angle theta, then this component would be Fg cosine theta, and this component would be Fg sine theta, then minus Fg sine theta. And notice that we're asked to express the expression of the magnitude of the centripetal force in terms of theta. So basically sine theta is accepted. Don't expect that they will ask you to express in terms of sine and cosine, because these are functions. And the magnitude of the forces, which is basically the normal push and the pull of gravity, that already have been represented in part A. So basically this is it for part B. Now in part C, we need to derive an expression for the speed Vd of the passenger compartment as it reaches point D in terms of mr and fundamental constants as appropriate. By fundamental constants, so basically they're referring at least for the gravitational field strength G. Now we need to determine the expression of the speed at the point D, and notice something that I have stated at the beginning of the exercise, that from A to D it's frictionless, which means that we can use the conservation of energy. If we take the PE level to be at this track, at the horizontal track, now at point A, the energy is purely gravitational, given by mgh, where h represents the vertical height from point A to point D, which is basically, so h would be 3 over 4 r plus r, which is basically 7 r over 4. And at the point D, the gravitational potential energy is 0, and the energy is completely kinetic, so we can use the conservation of energy from A to D. And for that reason, let me say take the PE level to be along the horizontal track, and now because we're applying a big law, I need to mention apply conservation of energy. And pay attention, usually the statement they give it half a mark because we're applying a big law. We're applying the conservation of energy between the points D and the point A that represents the final and the initial point respectively. At the point D we have kinetic energy plus gravitational potential energy, and at the point A we have kinetic energy and gravitational potential energy. Now that would be 0 because we're starting from rest, and that would be 0 because we have chosen the PE level to be along the horizontal track, and we have half capital M Vd square. We need to use capital M and not small m. That would be mgh, and between brackets let me write h is 3 over 4 r plus capital R, which is basically 7 over 4 r. And now here in this case m cancels, and we can say that the speed at the point D is given by the square root of 2gh, and this is expected because it's a complete free fall with no friction, with no initial speed, and that would be the radical of 2g multiplied by 7 over 4 multiplied by r, and that would be the square root of 7 over 2r multiplied by g. Then we can summarize our result by writing the speed expressed in terms of at least mr and fundamental constants as appropriate. Notice that here m doesn't enter in the expression, that's fine. Okay, then that would be our result. Now in the following part, before we reach part D, they are stating the following: a force acts on the compartment between points D and E and brings it to rest at point E. Now here, which force might be responsible for this stopping? We have two choices: either the friction between the compartment itself and the horizontal track, or it might be due to drag force, which is basically exerted by the fluid, which is the air surrounding the compartment. Now in part B, they're telling us if the compartment is brought to rest by friction, calculate the numerical value of the coefficient of friction mu between the compartment and the track. Now here by mu, they're referring to kinetic coefficient because there is relative motion between the compartment and the track, and this can be solved by two different methods. Either we can consider Newton's second law, or we can consider an energetic approach using work energy theorem. And let me say apply work energy theorem and the work energy theorem states that the variation in the kinetic energy is equal to the work done by all the external forces. Now along the horizontal track, let me refer back to the figure. From points D to E, if this is the compartment, what would be the forces acting on the compartment? We have the pull of gravity down, the normal push is up, and the friction opposite to the motion. Now the pull of gravity and the normal push, they perform no work because they are perpendicular to this horizontal track. Now the stopping is due to the work done by friction only. Now the final kinetic energy would be 0. So let me state them explicitly: the work done by gravity plus the normal push plus the friction. So that would be 0 because at point E we would be at rest, and the kinetic energy at the point D would be due to the speed at the point D, which has been determined in part C. So that would be minus half mvd square equals, this is 0 and that's 0, plus remember that the work done by the friction is always given by minus f dot d, which is times d, which is minus mu k, the normal push multiplied by d, and here the normal push, it's not modified, it's given by mg. So that would be minus mu k, or mu as it's given here, the normal push, or let me say minus f dot d. Now the minus with the minus cancel, that would be half mvd square minus, mu mg or let me say the normal push multiplied by d, and that would be half mvd square, which is equal to mu m capital M gd. Now d would be the distance from the points D to the point E, and that is given in terms of 3r. So let me replace d by 3r. Now m would cancel, and we would have half Vd is given by 7 over 2 Rg equals to mu G 3R. Now G with G cancel, R with R cancel, and that would give us mu. So let me be more precise, that would be 7 over 4 is equal to 3 mu, which means mu is given by 7 over 12. And plugging that on the calculator, mu is given by almost 0.58. And remember that mu has no unit. Then mu is given by 0.58, which represents the coefficient of the kinetic friction between the compartment and the surface. Now let's move on to the next page. They're telling you in part E, now consider the case in which there is no friction between the compartment and the track, so we're gonna switch friction off, but instead the compartment is brought to rest by braking force given minus kv, where k is a constant and v is the velocity of the compartment. So here they have modeled a new force, which is given by the braking force, in analogy with the force that we have stated previously, which is basically due to air resistance exerted by fluid. Express all algebraic answers to the following in terms of m, r, k, vd, and fundamental constants as appropriate. So now whenever we derive an expression, we need to double check that it's being expressed in terms of these. Right, but do not solve the differential equation for v. We know that differential equations are obtained using big laws, and whenever we're talking about drag force or braking force modeled by velocity, we need to apply Newton's second law. Then apply Newton's second law, and we know that Newton's second law is a vector equation, and usually it's coupled with an FBD. So let me here represent an FBD that represents the compartment along a point between D and E. What are the forces that are acting on the compartment? We have the pull of gravity down, balanced by the normal push, which is up, and the drag force or the braking force would be acting in a direction opposite to that of motion. Let me say that this is Fd. Now Newton's second law is given by F net equals to ma. Now we have the pull of gravity, normal push, and the drag force equals to ma. Now remember that this is a vector equation which gives the birth of two linear equations along each direction. Now we're gonna project that along the direction of motion, which is the horizontal. Then projection along the horizontal, and that would be 0 plus 0 minus kv equals to ma. And here we're interested in determining differential equation for v. Then a can be related to v via calculus, which is a dv by dt. Then minus kv equals to m dv by dt, which means m dv by dt plus kv equals to 0. And let's represent it in a neat form, given by dv by dt plus k divided by m multiplied by v equals to 0. And this is a first order differential equation because the derivative appears to be in its first order form. And remember that they told us just to write the differential equation and not to solve it. Now in idea number 2, we're interested in solving the differential equation, and this can be solved by the separation of variable. Now let me start by saying that dv, and also let me check the following, that our differential equation indeed is expressed in terms of mrk as stated. Now dv by dt equals to minus k over m multiplied by v. Now let's separate the variable v alone and t alone. That would be dv by v equals to minus k over m multiplied by dt, and now we can integrate safely on both sides. Now that would be ln v, which is equal to minus k over m multiplied by t, and here we can include the constant only once, but remember that we're interested in v and not the ln of v. Then we can consider the exponential of both sides. Now using the identity, e to the power of a plus b is given by ea multiplied by eb. Now if c is the constant, then this can be again stated to be itself a constant. Then that would be, here e and ln are inverse function, they cancel, so that would be v equals to c e minus k over mt. Now it's left to find the constant c. Starting at the point D, which represents our instant, then initially at the point D our speed is given by Vd and not 0. We have initial speed. Then now we can say that at t equals to 0, that would be Vd equals to c e power 0. E power 0 is 1, which means that the constant c, the constant of integration, is given by the speed or the velocity at the point D. Then our velocity or the speed as function of time is given by Vd. So let me state it like that. Multiplied by e minus k over m multiplied by t. Now on the axis below, sketch a graph of the magnitude of the acceleration of the compartment as a function of time. On the axis, explicitly label any intercepts, asymptotes, maxima or minima with the numerical values, all algebraic expressions as appropriate. So we need to do the plot for the magnitude of acceleration, and this is a bit tricky because they're asking for the magnitude of acceleration. Acceleration is a vector quantity, and the results might be different whenever we're talking the magnitude of the vector or the vector itself, whenever the vector quantity we're talking about is negative. So first let's determine the acceleration. If our speed is given by, or velocity is given by vd e minus k over mt, then the acceleration is given by dv by dt, which is basically d by dt of vd e minus k over m multiplied by d. Now vd is a constant, can be dragged out. Now what about the derivative of this exponential function? We would multiply by the inner derivative, which is minus k over m e minus k over m t, and the acceleration would be given by minus vd k divided by m e minus k divided by m t. So remember that also we know how to plot three different exponential functions given by 1 minus e minus box, which represents an exponential growth up to an asymptotic value, and e minus the box, which represents a positive decaying exponential function, and minus e minus box, which represents a negative growing exponential function, like that. Here, if you want to plot this function, the graph would be something like that. However, we're not interested in drawing this function, but the magnitude of this function, and by that we would multiply by an additional minus sign because all of this is positive, and the graph would look something like that, starting from an initial value given by vdk divided by capital M. And notice that we can express our answer in terms of vdk and m as stated in part E. And also let's double check that our velocity is expressed in terms of vdk and m as stated here. Then the magnitude of the acceleration would look something like that. This is the initial acceleration given by vd, the magnitude, vdk divided by m, and it will decay in the following form. And by that we have finished the exercise. So thank you for watching and see you soon in a new one.